Okay, we're going to do a quick example of implicit differentiation. And this problem, we want to find dy dx, and we're given an expression that involves x and y is involved implicitly. If you remember, an explicit relationship is usually y equals stuff with x's. But it's just y equals, and then there's only x's over here. There's no y's involved over there. When you have y sort of showing up in multiple places, or even here, this is like inside of another function, it's not y equals something, that's when you're going to need to use implicit differentiation because y is implicitly defined. Okay, so to do this, we're going to take derivatives, and whenever we take derivatives of a term involving y, we're going to write down dy dx next to that expression. The reason is that y actually depends on x. So if I were going to compute the derivative with respect to x here, d dx, I need to actually do chain rule, where y is the outside function, and then I have like x on the inside. So I would have y prime, but then I also need to put dy dx. Okay, so let's go ahead and do this. We're going to differentiate both sides of the equation. So I'm going to take the derivative of cosine xy, and I'm going to take the derivative of secant x squared plus 3x plus sine y. Okay, to differentiate both sides. Over here on the left, I need to take the derivative of this, and I need to decide what derivative rule to use. Well, I have a cosine, and then I have things inside the cosine. So I'm going to start out with using a chain rule for this one. That tells me I need to take the derivative of the outside function. So maybe I'll write that explicitly. The outside function is like cosine, and the inside function is x times y. Well, the derivative of the outside function is negative sine, and the derivative of the inside function is going to require us to use the product rule because I have x times y. Okay, so the product rule tells us take the derivative of the first expression there, so x, derivative of x is 1, times the derivative of the second part. Here it's just y, just times y by itself, so we leave that alone, plus the first part of the product, that's x, times the derivative of the second part. The derivative of y is 1, and then I need to write dy dx next to it. Okay, so let's put this all together. We're applying the chain rule. So I have, remember the chain rule says if I'm taking the derivative of f of g of x, I write the derivative of f evaluated at the inside function times the derivative of the inside function. So the derivative of the outside function was negative sine x, but instead of x, I need to evaluate it at the inside function, which here is xy. Okay, so that's the derivative of the outside with the inside plugged in, times the derivative of the inside function. We just took that derivative here. So times y plus x dy dx. Okay, so that is the derivative of the left-hand side of this expression. I still need to differentiate the right-hand side. Okay, so if we're going to compute this derivative, we need to compute the derivative of each term. So I need the derivative of secant x squared plus 3x, and I need the derivative of sine y. Okay, the derivative of this first expression, I need to use the chain rule again. I need the derivative of the outside, which is secant, the outside function is secant, and the derivative of that is secant tangent But instead of just putting x's inside, remember this is the derivative of the outside, instead of just putting x's in here, I need to evaluate at the inside function. The inside function here is x squared plus 3x. So I put x squared plus 3x wherever there would have been an x in my derivative. Then I multiply by the derivative of this inside function. The derivative of that is 2x plus 3. Okay, so that takes care of this term. Now I need the derivative of sine y. Well, the derivative of sine is cosine, but this expression involves a y, so I need to write down dy dx next to it. Okay, so let's put this all together. On the right-hand side, I had the derivative of this expression. So let me give myself a little bit more room here. So I have secant x squared plus 3x tangent x squared plus 3x times 2x plus 3. That's all coming from this computation. Plus the derivative of this expression, which we found was cosine y dy dx. Okay, so I've taken all the derivatives. Now I need to solve for dy dx because we were told to find dy dx, which means our answer, should be dy dx equals stuff, whatever we find. Okay, so our answer should be written in that form. So at this stage, I need to solve for dy dx. Maybe the easiest way to do that is to group everything that has a dy dx on one side and then factor it out and divide. So let's get all those things on one side. First, I'm going to go ahead and distribute this expression. So I had negative y times sine xy. That's just me multiplying the first two terms there. Plus, or I guess minus, because it's minus sine xy times x times dy dx. That's me multiplying that expression. And I don't really like having the x over here, so I'm going to go ahead and put that in front of the sine term here. Okay. You don't have to do that, but I prefer having that in that spot. Okay. And then over here, I don't really have much to change. I just have secant x squared plus 3x tangent x squared plus 3x. And maybe again, whenever I have trig functions, I like to put stuff that's not a trig function sort of in front. So maybe I'll put the 2x plus 3 in front of this. You don't have to do that. It's just kind of a preference that I have. I'm doing these kinds of problems so many times, but you can leave it however you want. And then we have plus cosine y dy dx. Okay, so I have two terms here that have a dy dx next to them, and I have a bunch of other terms that, oh, I guess it's just two, it just looks like a lot. I have two other terms that don't have dy dx's. I'm going to get all the dy dx terms on the left side, and I'm going to put all the stuff that doesn't have dy dx on the right side. So I need to add and subtract stuff, kind of like you're solving equations for variables. I'm just going to move stuff around. So let's subtract cosine dy dx from both sides. So I have negative cosine y dy dx on the left. So minus x sine xy dy dx. So those were my terms I was sort of collecting that had dy dx next to them. And I want to get this y sine xy over to the right, and it has a negative in front, so I'm going to add y sine xy to both sides. So on the right, I'll have y sine xy, because I just added that over, and then plus all this other stuff that I already had over there. squared plus 3x. Okay. And so these were all the things I had highlighted in pink. Great, I'm almost there. I'm trying to get the dy dx by itself. So here, both of these terms have a copy of dy dx. I'm going to go ahead and factor this out. I'm treating it like a variable that I'm trying to solve for. So I'm going to go ahead and factor it out of this expression. So I have negative cosine y minus x sine xy times dy dx. Just factor that out. And then I don't feel like writing this, so I'm going to copy and paste it. It's the same expression as before. So there, maybe I'll get rid of the, oh, hold on. Now I can get rid of the highlight. All right. Now that I have dy dx sort of on the outside here, multiplied by something, I can divide by this whole expression here to get the dy dx by itself. So I'm going to divide by negative cosine y minus sine xy on both sides. That's going to leave me with just the dy dx on the left, and then I'll have this big fraction over here on the right, and that's fine. So dy dx equals, my numerator is just all the stuff that was already on the right-hand side. 2x plus 3 secant x squared plus 3x tangent x squared plus 3x. All of that divided by this expression, negative cosine y minus x sine x y. And at this point, I am done. That is dy dx for this relationship. All right, that's how you do implicit differentiation for a problem like this. Let me know if you have any questions.